We might have just lost the recording in the first few minutes. I guess that's probably okay. A quick comment came in on the back channel. Will the homework be posted on Carmen? Yes, it will be posted. Thank you to whoever responded to that in real time. That's great. Okay, here we go. So again, we're talking about ways of numerical summaries of talking about our data. And the first one we're going to talk about is measuring the center. So before we had talked about, when we're looking at a distribution, we're talking about the center of that distribution. And the first way that we're going to do that is by using the mean, or the arithmetic average. And this is the same mean that you've seen many other times before, I'm sure, in your other classes. In this class, our notation is going to be, this is going to be our notation for the mean. And that's just pronounced x bar. So that's what we're going to call the mean, and what that means is just that we're going to take all the numbers that we have in our data set, add them up, and divide by the total number in our data set. So some fancy notation down here. If each one of these things are our observations, x1, x2. So if I have 10 of you, for example, and I want to calculate your average height, I'll take each one of your heights, add them all up, divide by the total, and get my average. This notation over here, this capital sigma, just means that we're going to sum over the data. So I'm not trying to confuse you with a lot of notation here, but this is what the mathematical notation is. And as I mentioned briefly on Friday, I think you can also think of the mean as being the center of mass, or the balancing point. So if you think about our distributions that we were looking at as a solid shape, the mean would be right where that shape would balance on there. If you want to think about it, that way. So this is our first way of talking about the center. Excuse me one moment. So our other way that we'll use to talk about the center of a distribution is what's called the median, and this is probably familiar to you guys as well. By definition, here it's the midpoint of the distribution, just the number such that half of the observations are larger and half the observations are smaller. If you've heard, I'm sure you've heard, if you're driving down a highway, that strip of land in the middle is called the median. So maybe a good way to keep that in mind is just that. That median strip in the road is just right in the middle of the road. So think about, similarly, if you have a list of numbers, the median is that number that's right exactly in the middle. So again, calculating the mean can be fairly straightforward. Calculating the median can be a little more tricky. So let's talk about how we might go about doing that real quick. The first thing you want to do when calculating the median by hand, which we won't always do, but we'll do here now to kind of understand how that's done. The very first thing, it's very important that you need to do, is put all the numbers in order from small to large. And then this second bullet point, let's skip over for that a minute, and I'm going to focus in on this third one. It's kind of two alternative ways of finding the median. I think the third bullet point's a little easier, but you can do whichever one you want. So once we have our list of numbers in order, we can figure out how many total observations we have. So n is the total number of observations that we have, and that's going to be our notation throughout this class here. So if you just add 1 to the total number that you have and divide by 2, that will give you the position of the median. So remember, you have the numbers in order, and if you can find which position it is, you can just count up to where that number is. A question just came in on back channel. Says, just to refresh, the graph can have multiple means as well as centers, and so should we give separate means or separate measures of center? Very good question, and yes, we will want to do that. I'll tell you to hold on to that question until we have an example where we'll be looking at that in just a minute, and I will come back to that question. Thank you, though, for that question. Okay, so here's our two measures of center. We're going to talk about the mean, and we're going to talk about the median. And here we've just briefly mentioned how to calculate these. Let's go ahead and do an example here to actually put these into practice and show you what I'm talking about here. So the example we're going to do here is a little sports example, and we're going to look at the roster for the NBA for the Chicago Bulls, excuse me. And just a little note that they do have Nate Robinson last year anyway played for them. I think does he still play for the Bulls? Does anybody know? Did he get traded? He get traded? Who made that comment? Plays for the Nuggets now. Okay. Well, then I should have updated my information. But thank you. Anyway, he's one of, if not the shortest player in the NBA, and so we'll just use that fact in a moment here. If you downloaded the notes, the program heights are listed in there. I didn't include them here, other than as well as all the players. What I've done here is put them in order. So what we want to do now with this example is, for this list of numbers, we want to calculate the mean and the median. So going back to our strategy from before, the mean, again, our notation is going to be x bar. That's what we're going to call the mean. And again, as usual, we're just going to add all these numbers up, divide by the total that we have, and see what that gives us. So this is we can write this out as 69 plus 74 plus 75. I'm going to get lazy and put some dots there, just indicating that we're going to add up all the numbers that are in that list. So we're going to take add 76, 77, 79, 79, 81, 81, 81, and all the rest of them there, finishing up with 82 and 83. And then we want to divide by the total number of observations that we have, which here, I think if you double check and count, that's going to be 13. So if you take out your calculator and punch all these numbers in, this is 1019 divided by 13, or 78.4 inches. So that is the mean, that is the average height for this basketball team, 78.4 inches. So now let's calculate, let's also calculate the median, so we can practice doing that. And again, we're gonna use that third rather bullet point there. So we're gonna take our number of observations, add 1 to it, and divide by 2 to give us the position of the position of which the median, where the median is. So here we have n plus 1 divided by 2 is 13, plus 1 divided by 2 equals 7, so that the median is in the 7th position. And if you count over, again, remember that it's very important to have the numbers in order. So I've done that for you here, but you might have to do that on your own if you're trying a new example. Count over to 1, 2, 3, 4, 5, 6, 7. It gives us that the median is 79 inches. Any questions on how we calculated either of these things? Feeling pretty straightforward? Yeah. Okay. Well, let's try it one more time here. And since Nate Robinson since he's a fairly short player, he's only 5'9". Let's take his number out of there and calculate these things again and see kind of what happens. So again, we have the same data set. We've just taken out the smallest observation. We've removed the 69 inches from the height there. So let's again calculate the mean. Again, this is going to be x bar, what we're calling that, 74 plus 75 plus so on up to 83. And we want to divide by the total number of observations we have, again, which is, now we've taken 1 away, so we only have 12 people listed here. And if you work that out, that is 950 divided by 12, which is 79.2 inches. So again, pretty straightforward, not really anything different going on there. For the median, though, Our n is now 12, so when we take n plus 1 divided by 2, this is now 12 plus 1 divided by 2, which is 7.5. So does anybody see the 7.5 fifth number on there? Thank you. Check my math here. In any case, can anyone tell me where the 6.5 number on that list is? Well, of course not, right? We only have even or whole number places there. So this will often be the case. So what you want to do, again, remember we want the median to be the number that's exactly in the middle. So the middle here falls between the 6th and 7th number. Change my color here. So so those two numbers are sort of around the middle of the data set. So when you have an even number, what we can do is take the two numbers on either side of 6.5, so the 6th number and the 7th number, and average them together. So here, this just means that we want to average the 6th and 7th number. So again, we want to find that number that's exactly in the middle. So what we can do is take the number that's between these 2 points in the middle. So now m is going to be 79 plus 81 divided by 2, or 80 inches. Again, pretty straightforward, a little tricky since we have an even number of observations. You're going to have to do this little trick to get the median here. Any questions you guys can think of on calculating the mean or the median? Okay, great. Oh, question just came in. Must the median always be a whole number? And the answer is absolutely not. So if we had numbers that were more than 2 apart here, your median can be any number. And it's also important to note that the median might not always be a number that's in your data set, right? So there's nobody on this team who's 80 inches tall, right? And yet that's still the correct answer for our median. So both the mean and the median could be, of course, a fraction or not a whole number. Could be a decimal in there as well. And again, note the median might not be a number that's actually in your data set. So just an important, great question. And do we need to be this explicit with all the steps in the homework? Probably not. It's definitely good to show work, because if you've gotten something, if you made a mistake in there, we can give you partial credit, but I'm being a little bit more thorough than you probably need to be in your homework assignments. Again, just kind of working through the calculations at this point to get an understanding of what these things mean. But thank you for the questions. All right, so this is coming back to that question that came up. You guys are ahead of the ball all this time here. So what if we have a distribution here that is bimodal? So again, if we're rewinding to Friday when we're thinking about describing distributions, if we were looking at this histogram, again, if you draw sort of a smooth curve to it, you can definitely see that there's sort of these two points, these two peaks going on here. So we have a bimodal distribution. So just to kind of review what we talked about on Friday, let's quickly describe the shape and center of the histogram. I've already told you that it's bimodal. Is the shape of the distribution. And so maybe I should quickly mention what we're looking at here. Should have done that first, sorry. So what we have here is a histogram of the ideal height in inches of people in a previous Stat 1450 class. So if I could ask, and maybe I'll ask you guys a question. So why would you expect this to be bimodal? Why would you expect this histogram to look like it does? Say that louder. Right, okay, so we have both males and females in this class. And most likely you would expect that males would, on average, have their ideal height be a little higher. females their ideal height would be a little lower. So that's kind of why this bimodal shape is not surprising. So okay, so we have this bimodal distribution, and then well, let me quickly ask you guys see any outliers on this histogram? Pretty obviously, right? We have this strange person out here who has said that their ideal height is 96 inches or 8 feet tall. I don't know. I'm not sure that I would want to be 8 feet tall, but maybe somebody does. So this is definitely an outlier going on out here. Okay, so we have a bimodal distribution that is fairly symmetric. If you sort of ignore this outlier point, it's sort of symmetric. We'll say approximately symmetric. And then we want to talk about two measures of center. Remember, we have two modes, so we want to mention what each of those centers are, sort of those high points in the graph. So again, when we're talking about calculating numerical summaries, if we don't have the data in front of us, there's no way we can actually calculate what these two measures of center are. What you would need is a list of all the responses with an indication of which gender each response was. You need a list of all the female responses for ideal height and all the male responses for ideal height. And then you could do the same thing that we just did and calculate the mean and the median. Here we don't have the numbers in front of us, so we'll forgo that step for now and just kind of go back to what we did in chapter 1 and just mention that we kind of have these two centers happening here. So we have two centers. The males are centered around, I don't know, let's say 74 inches. And the females are a little bit lower. They're around 66 inches. And that's just an assumption we're making that there are these two groups sort of naturally happening. You don't have to always say what the groups are, but again, it is important to say. In other examples, it might not be as obvious what the two groups are, but it is important to sort of mention that there are these two measures of center and kind of say what they are. Another question came in, is there a rule of thumb for how many decimal points to put on our homework? There is no rule of thumb. 2 to 4 decimal points is probably good, depending on how big the rest of the number is. But definitely no more than 4 are needed. So if you put more, we're not going to dock you off. I've seen a lot of times on homeworks and exams where someone puts 8 or 10 decimal points, which is probably more than you need. But yes, so I would say, what I would say though is as you're doing calculations, if you're doing it on your calculator or something, don't round as you go. Round the numbers off at the end. So kind of don't do any rounding until you get to the end of your calculation. And then otherwise, 2 to 3 or so is fine. Yeah. Can you round? Sure. Yeah. So you're welcome to when you're writing out your work, you don't need to write 10 decimal points at each step. Kind of put what approximate the number is, and then round for the last step. If you want to make a note of that, that's great. You would not have to do that though. Yeah. Okay. So just remember that when we have a bimodal distribution, you want to make sure to talk about both measures of center. And if we actually had the data, we could calculate what those measures of center are for each of the groups. All right, so let's take a minute to kind of compare these two measures of center. Again, at the beginning I said we're going to have multiple ways of talking about each thing, and let's figure out which one is appropriate to use when. So when we have a symmetric distribution, if the distribution we're looking at is roughly symmetric, the mean and median will be very close together. And if the distribution is perfectly symmetric, as this picture is, so there's that spot in the middle is a perfect reflection point, then they will be exactly the same thing. So on this picture here, both the mean and the median are right here in the middle. Again, that looks like the balancing point for that shape, if you were to imagine that as a shape. But you can also see that it's the number that's exactly in the middle of all those of that shape. So when you have a roughly symmetric distribution, they will be about the same. If we have a skewed distribution, remember this is something else we talked about. If if some numbers trail off far to the left, or if some numbers trail off far to the right. So if you have a left skewed or a right skewed distribution, we're going to say the mean is usually further out in the long tail than is the median. So there we have a picture. It's labeled where the mean and the median is. The mean is going to be further out towards the tail of the distribution than the median is. Can anyone give me some intuition on why that might be the case? Why the mean might be sort of pulled out into the long tail there? Yeah. Okay, so the response with the outliers could be very large or very small depending on which case we're in up here, and so that will affect our numbers. And how does that? I guess can you take that one step further? You're exactly on the right track. Exactly. Exactly right. Okay, so the point is that the median, the response was that the median is not affected by these larger numbers, right? The median, we're just counting up a position, and if you change the biggest number, if you added 100 onto that one, the median would not change at all. Whereas the mean, if you remember our calculation, we were adding up every single number. So every single number goes into the calculation of the mean. Let's make a quick note of that. The mean uses all numbers in its calculation, which means that it's affected by extreme values. So again, because every single number goes into the calculation of the mean, if you have one really large number or one really small number, that's going to have a big effect on the mean, whereas the median will be unchanged in some of those cases. So just keep that in mind, that the mean will always sort of go out into the tail if you have a skewed distribution like this, and the mean will be sort of, the median rather will be sort of unaffected by extreme values. All right, so I guess we sort of just talked about this, but quick show of hands, which measure of center is resistant to skew and outliers? So this is a slightly different way, but how many of you think it's the median? I said those in the wrong order. How many of you think it's the median here? And how many of you think it's the mean? Okay, so I tricked you, but you were paying attention, so that's good. Didn't mean to do that. So the median is the number, is the one that is resistant to skew and outliers. So just kind of reiterating that same point that we just discussed. All right, so we'll close our discussion for now on measures of center, and now we want to talk about measures of spread. If you remember on Friday when we were talking about the spread, we sort of just talked about the range. So we were looking at the highest grossing movies from a few years ago, and we simply said those ranged from about 50 million to 400 million or something like that. And we're going to talk about some other ways of how to talk about spread. And the first way we're going to do that is through something called the quartiles and the IQR, and I'll say what that is in just a second. So what the quartiles are here, the first quartile, which we'll call Q1, by definition here, it is the value in the sample that has 25% of the data at or below it. Similarly, the third quartile, Q3, is the value in the sample that has 75% of the data at or below it. So that's I think a little tricky. Maybe this picture will help you. So if you think about again, we talked about the median. So this half down here is going to be 50% of our data, whereas this half up here is also 50%. It's helpful, I think, to think of the quartiles Q1 and Q3 as sort of the median of the smaller and larger half of the data. So the first quartile here, this is the median of the smaller half. And similarly, the third quartile is if you think about that as being the median of the larger half of the data. So if you put your numbers in order as we did in that previous example, this is kind of the spread there. And yes, another name for the median is the second quartile. If that helps you, you're welcome to use that notation, that terminology. We usually just call it the median, though. So that is officially what it's called. So let's jump back a slide here to talk about how we actually calculate these things. Again, what we want to do is arrange them in increasing order from small to large and pick out the median. And then to find the first and third quartile, again, we sort of ignore the larger half of the data, just looking at the smaller half, and pick out the median in that smaller half. That's your first quartile. And then do the same for the larger half, and that's going to be your third quartile. And a note, which we'll look at when we do an example here in just 1 second, is that when there's an odd number of observations, you can leave out the overall median when you pick out the quartiles. So I'll show you exactly what I mean by that in just a second. All right, so let's actually try to go about doing this now. Again, we're going to stick with the same example, and we're going to leave Nate Robinson's height in there. Again, we have the program heights for the Chicago Bulls from last season. And if you remember, we picked out the seventh number, 1, 2, 3, 4, 5, 6, 7. This is our median. And again, remember that we have 13 observations here. If you count up all the numbers there should be 13 there. And now we want to calculate the first and third quartiles. So if thinking back to the note that we just mentioned here, when we have an odd number of observations, leave out the overall median when we're calculating the quartiles. So now we just need to find the median of this group and the median of this group. And note that I'm leaving out the overall median when I'm doing this calculation. So let me change colors here. So again, now each half only has 6 numbers, so we can just kind of look at it and see that these 2 numbers are in the middle. Similarly, these 2 numbers are in the middle. So Q1 is going to be the average of those 2 numbers in the middle, just like we're calculating the median now of 6 numbers, kind of like we did before. So that's going to be 75 plus 76 divided by 2, 75.5. And here the third quartile is going to be the average of those 2 numbers. And those are going to be our quartiles for this data set. So again, all I've done is I've taken the smaller half of the data, so it's these 6 numbers that I have on the left there, and I've found the median of those numbers, which is then our first quartile. Then I look at the larger half of the data, and I find the median of that half, and I get the third quartile. So we've been doing all these by hand, and I think that's very important. It's good for you to kind of get a sense of what these things are and sort of what they mean. The good news is here in the future, or definitely if you have a larger data set, so say you have 142 numbers, you don't want to take the time to put all those in order and count through and all those things. So we're going to use technology in general to find these things. But just again, working through the calculation so that you know exactly what we're talking about here. Any questions you guys can think of on calculating quartiles? Feeling okay? Okay. So then to actually measure the spread, we're going to use something called the interquartile range down here at the bottom, which we can also use to spot suspected outliers. So far, we've sort of picked out numbers that look like outliers. We haven't had a real good way to say definitely this is an outlier or this is not an outlier. And now we're going to have a rule of thumb for doing that. And this is one way to do that. And so what we're going to use is this thing called the interquartile range, which is simply the difference between the first and third quartile. So the two numbers between which 50%, the middle 50% of the data lies. That's our interquartile range. So quickly, let's say, what is the IQR for this example we've been working on? Well, again, it's just the third quartile minus the first quartile, which was 81.5 minus 75.5. And that's going to be 6 inches. So the interquartile range here for this example is going to be 6 inches. And then the rule that we're going to use to try to pick out if numbers are outliers in our data set is this thing called the 1.5 times the IQR rule for outliers. So we're going to flag observations as suspected outliers, and then we'll go investigate those data points to see, was it a typo? Is this someone recorded a bad data point? Or maybe this is maybe somebody really did want to be 8 feet tall in their ideal height. So an outlier doesn't always have to be wrong. It might be something that you need to take into account. But again, we're just looking at a way to spot these suspected outliers. And so what this rule says is that a suspected outlier lies below this value or above this value. So we're going to take 1.5 times the interquartile range, subtract it from the first quartile, that's sort of our lower bound. And then we're going to also add that to the third quartile, and that's going to sort of be our upper bound. So numbers that fall outside of those numbers, we're going to flag as suspected outliers. So now we have an exact rule of saying, yes, this point is an outlier, or no, it is not. So going back to our same example, and remember that we do have Nate Robinson in this data set, who we know to be sort of a very short player relative to the rest of the NBA. And so let's ask this question, are there any outliers in this Bool's height data, at least according to this rule that we just mentioned? So to do this, let's first figure out what these numbers are. So we have 1.5 times the interquartile range. That was 1.5 times 6, which equals 9. And then so our lower bound is going to be the first quartile, Q1 minus 1.5 times the IQR. Our first quartile, again, was 75.5 inches. Subtract off 9. And we have 66.5 inches. That's going to be our lower bound. If we look at our upper bound, we'll take the third quartile plus that same number. And that was 81.5 plus 9, or 90.5. So these are sort of our bounds, right? So if we have any observations in our data set that's less than 66.5 inches, we're going to call that an outlier. If we have any numbers larger than 90.5, we'll call those an outlier. So do we have any outliers in our data set according to this measure? If you look back to the list of numbers, I see some shaking heads. You will see that there are no numbers less than 66.5 or bigger than 90. So at least according to this rule, we have no outliers. So even Nate Robinson is not considered an outlier according to this rule. All right, so this takes us to one more thing to mention, one more sort of numerical summary that includes a few things, and this is called the Fivenumber summary. This is similar to actually that little picture I put up earlier. But the Fivenumber summary of a distribution consists of 5 things. It consists of the smallest observation, the first quartile, the median, the third quartile, and the biggest observation. And so in symbols, kind of looking at it as we've done before, that's how we'll denote each one of those things. So what is the Fivenumber summary for the Bool's program heights? Well, we already know the first quartile was 75.5. The median, remember, we found was 79. These are all inches. The third quartile was 81.5 inches. And then going back to look at our data, remember we have it in order, so we can just pick off the smallest and largest numbers. So the smallest we had was Nate Robinson, 69 inches, and the largest was 83 inches. So that's something that is very easy to get from technology and can be a good summary of the distribution that we have. And we actually have a way of visualizing this 5-number summary, and we can visualize this through something called a box plot, and it just gives us a graph of the 5-number summary. So I'll show if you're looking at your notes, there is a picture there of what a box plot looks like. This box in the middle covers the middle 50% of the data. The line in the middle marks the median, and then the lines extend from that box out to the smallest and largest observations. And there, we also do have something called a modified box plot, which shows suspected outliers as dots or an asterisk or something like that. Very good. So let's take a look at what the what a box plot looks like. So if you use jump and you ask it to create a box plot using this data, this is what it will give you. And just to point that this number here in the middle, this is the median. This is the first quartile. This is the third quartile. This is the max, and this is the min. So again, it just gives you a way to visualize quickly what the 5-number summary looks like, and this is called a box plot. When I've taught this class previously using jump, people have asked what the red bracket means, and I never actually knew what it was, so I actually looked it up this time. And that refers to the shortest half of the data, or the densest region. So this is the shortest half of the data, or the densest region. So don't worry about that at all, but if you're curious on what that is, that's just showing you which range contains the densest sort of 50% of the data. Question back there? Does the diamond in the middle have any significance? I don't know. I don't think so. Most box plots, you would not need to put that there unless you want to be fancy or something. But no. Or if it does have a significance, I couldn't find what that was. Yeah. Thank you. That question came in on the back channel as well. Sorry, don't have the answer to that one. And just one more slide here before I let you go. Just to note that a box plot can help us show kind of the skew of the data to see if it's symmetric or skewed in one direction or the other. The picture there on the left is a picture of what a skewed right distribution is. So you can kind of think of this as corresponding to a histogram that looks something like this. And over here on the left we have a skewed left, so this would look something more like that. And so the box plot can help us quickly see if we have any skew going on. But just note there that if we do have a bimodal distribution or something like that, like we did with the ideal heights, the box plot will not show us what that will not tell us that there's any modes. So again, this is not a complete way of looking at the data, but it's just another way to visualize things. Any other questions before I let you guys go? You can think of? Great. Thank you guys so much for being here. Have a good rest of the day. We'll see you on Friday.